All right, these are the notes for Algebra 2, Section 2.5. We're looking at direct variation. Now, in the equation y equals a times x represents direct variation between x and y. We would say that y varies directly with x. That's the language we would use. Y varies directly with x. We need to know that because there are different kinds of variation, and we need to be able to identify them. So y varies directly with x indicates direct variation. Now, in the equation y equals a times x, a is a constant, right? We might have, for example, an equation like y equals 2x. A, in this case, would be 2, right? A, the constant of variation, of course, has to be a non-zero number. Can't be 0, otherwise the whole thing falls apart. And really the biggest challenge of a direct variation problem is figuring out what that constant of variation is. Now, I have a couple of graphs here. These two lines are both direct variation graphs. You'll notice that the graph of a direct variation is a line, and you can see here we have this line here starts at the center here, and it goes up 1 over 2, up 1 over 2. So it has a slope of 1/2. Right? The slope of 1/2 also happens to be a, the constant of variation. The y-intercept is 0. And it's the same for negatives. Here we have -1 for a slope. That is our constant of variation. Right? The constant of variation can be positive or negative. It can be 1, that's fine. It just can't be the number 0. What you should see is that the family of direct variation graphs, that is, every direct variation graph ever, consists of lines that go through the origin. See, both of these lines go through the origin, that magical point 0, 0. Both lines go through that. And in fact, every direct variation equation goes through the origin. Now let's see what we can do with direct variation. We're going to start by writing a direct variation equation. And like I mentioned, the biggest part of any direct variation problem is usually going to be identifying the constant of variation. And this is really no different. We want to write a direct variation equation that goes through the point -3, 2. Now you need to keep in mind that -3, 2 is x, y, the point xy. The way we would go about this is to substitute in the x and y we were given and use those to find a. Once we have a, we know the equation. So let's start. Y is 2, so we're going to substitute in 2 for y. X is -3, so we're going to substitute in -3 for x. And then we're going to solve the equation. Right? 2 equals a times -3. So we would divide by -3. Do it on both sides. They cancel out over there, leaving us with a equals -2 over 3. So the direct variation equation then is y equals a times x, and a is -2 over 3. So the full equation is y equals -2 over 3x. All right, let's put that into practice with a word problem here. Now we're talking about Hooke's law, and according to Hooke's law, we have force. And the force that is needed to stretch a spring varies directly with the amount the spring is stretched. So we have force and we have stretch. Those are the two things we're comparing. And you'll notice those magic words. They say it varies directly. And you remember, y varies directly with x. So, force varies directly with the stretch of a spring. Let's look at part A. Part A tells us that we have 64 pounds of force. And it stretches the spring a distance of 8 inches. So we have force, we have distance. What we do not have is a constant of variation. So that's what we have to find. Using the information we were given, of course, we can just plug that right in here. And we'll say, all right, well, we'll substitute in 64 for F because we have 64 pounds of force. We will substitute in 8 for D because we have 8 inches of stretch. And we will solve this equation. Divide by 8, and 64 divided by 8 is 8. So, A equals 8. That means that our equation is F equals 8D. Now, we can use this equation, F equals 8D, to answer part B here. Part B asks us to predict the amount of force needed to stretch the spring 14 inches. So, we're predicting force. We need to find F. Now, we know the constant of variation is 8. Right? The constant of variation is 8. We just figured that out. We also know that we stretched the spring 14 inches. So, we will replace D with 14. Now, of course, 8 times D, or 8 times D, or 8 times 14, we multiply that out, is 112. So our answer then, if we're stretching a spring 14 inches, then we would have to put 112 pounds of force to do that. All right, we have one last problem we're going to look at. Example 3 here. And what we've got is we're being asked to use ratios, fractions, to identify direct variation. We've got a table that has cell phone bills, cost versus minutes. Now, we want to tell whether the total cost and number of minutes show direct variation. So, does the cost vary directly with the number of minutes? That's the question. If it does, we want to write an equation that relates the quantities. So here's how we can go about doing that. We've got a table of values, C and M. We want the ratio of C to M. So we have these various points, right? 35 and 100, 45 and 129, 200 or 880 and 229, 15 and 44, 30 and 80. All of those are related values. The idea is this. The ratio, I'm going to write this down, the ratios of related values should be equal. The ratio of related values should be equal across the board. So the ratio of 35 to 100 should equal the ratio of 45 to 129, which should equal the ratio of 80 to 229, so on and so forth. Now there might be a little bit of give here and there because, of course, when we're dealing with real-world situations, sometimes we'll have a little bit of inaccuracy. Let's just call it inaccuracy. But for the most part, the ratio should be pretty much spot on. Now, how, you might be asking, do we figure that out? And that's a very good question. Here's how we figure that out. We look at, let's start with the ratio of 35 to 100. Right? The ratio of 35 to 100, we turn that into a fraction. We figure out the decimal is 0.35. Right? Calculator does that for us. So we have a ratio of 0.35. Let's see if that is equal to the others. If we have a ratio of 45 to 129, that is about, we have to round in this case because it's not completely accurate, about 0.35. And it's in fact 0.34 something that we can round to 0.35. We have a ratio of 80 to 229, which again, 0.34 something. So we will round to 0.35. Notice the pattern here. These ratios so far are all the same. I have 15 to 44, and that gives me a ratio of, this time, about 0.34. But that's still pretty close to 0.35, so we'll let that slide. I mean, it's not like it's 0.1 or 5 or something. And the last one we have 30 to 86, and the ratio of that, again, a little less than 0.35. It's not perfect, but it's just about at 0.35. So you'll notice all of these ratios are about the same. Since all of the ratios are about the same, this is direct variation. Now, since it's direct variation, we want to write an equation that relates to quantities. And this is where all the work that we've done kind of pays off. Now, since C divided by M, that's our ratio, C divided by M, since C divided by M equals about 0.35, that means that C equals 0.35 M. All I have to do is multiply both sides by M and get that over there. So that is our equation of variation.